Welcome to videos on data converters. Now here we are seeing unlock to digital converters. This is the second part of video series. So we were seeing in the previous lecture the quantization error. The quantization error comes into picture when the input voltage is gradually changing and we cannot assign for each and every changes of the input voltage. For every change there is no digital output. So for a voltage change from 0 to 1 volt, we have only 8 different combinations, that is from 000 to 111. So when it is the voltage is 0, the output voltage is 000. Even when the voltage is 1 by 6 so of a volt, 1 volt, so it is still 000. Anything more than 1 by 16th, so the output is the digital value is 001. So that will be 001 from 1 by 16 to 3 by 16. This is actually 1 by 16, this is 2 by 16, this is 3 by 16. When the input voltage is ranging from 1 by 16 to 3 by 16, the output voltage is still 001. So we know that there is an error in the representation of the output bit. So actually this would have been 001 only for the input voltage of 1 by 8. So we don't have any error here, but the error is positive when you are representing the output by 001 for an input voltage of 1 by 16. Whereas when the input voltage is 3 by 16, the output is still 001. So we are having an error of minus half LSB. So this is what we discussed in the previous video, and we are trying to find out what is half LSB is equal to. We know that LSB is given by V reference by 2 power n. Half LSB is given by not V reference, V full scale range voltage divided by 2 power n plus 1, and its RMS voltage, the RMS value of the error voltage, since the error voltage is like a sawtooth waveform, so it is half LSB divided by, because it is peak divided by the root 3 value, so this happens to be half of LSB divided by root 3. So half of LSB is nothing but VFSR divided by 2 power n plus 1 divided by root 3 happens to be the RMS value of this error voltage, quantization error voltage. Now that's what is EQ is also given by VFSR divided by 2 power n into root of 12. So upon doing this, now root of 3 into 2. So because out of this 2 power n plus 1, you can write it as 2 into 2 power n. So that 2 into root 3 happens to be root 12. So let us continue with this. If input voltage which is sinusoidal signal, we can actually find the signal to noise ratio by taking an input voltage whose peak amplitude is VFSR by 2. When the input sine wave whose peak amplitude is VFSR by 2, we can write its RMS as VFSR by 2 divided by root 2, because this is the peak voltage. So peak by root 2 happens to be the RMS. So that's what is the input RMS is given by peak, which is VFSR by 2 divided by root 2. It is peak by root 2. And we know what is the RMS voltage of the error, that is quantization error, which is nothing but VFSR divided by 2 power n into root 12. So that's what we saw in the previous slide. So this is what is the RMS value of the quantization error. So that's what we are trying to repeat. Then SNR maximum, because it is the signal divided by the noise. So noise is here in the form of error voltage, quantization error. So we are writing 20 log of 20 log to the base 10 the input RMS divided by 20 log to the base 10 the error voltage. So we are substituting what is VIRMS and EQRMS. So we are simply substituting the values of the RMS voltage of the input voltage, which is given by VFSR divided by 2 into root 12. Okay, 2 into this is actually root 2. Fine, this is fine. VFSR divided by 2 whole divided by root 2 happens to be the RMS voltage of the input, and this happens to be the RMS voltage of the error voltage. And upon solving that, so now you can see VFSR is there in both the cases. Now you can just cancel out. This is a very simple math, you can do it. And upon doing all this, so it comes out to be SNR, signal to noise ratio. That is, now here the noise happens to be the error voltage. Signal to noise ratio happens to be 6.02 plus 1.76 dB. So we are supposed to have the signal to noise ratio as high as possible. Now you can see it is 6.02 n plus of 1.76 dBs. Now what does this mean is, every increase in the value of n by 1, assume that n is now 3 bit, so we can find out what is SN or max. So it is substituting this n by 3, that is 6.02 into 3 plus 1.76 will be the signal to noise ratio. So if you increase the value of number of bits by 1, so signal to noise ratio will increase by 6 dBs. Meaning, if you are having larger and larger number of bits, the quantization error will be minimized, so that you are going to get a larger signal to noise ratio. So in order to have a better signal to noise ratio, the key is we are supposed to increase the number of bits in this ADC. Let us see what are the ADC errors here. ADC errors are defined in terms of the values of Vi at which code transition occur. So we know that code transition will occur here. The transition is occurring at 1 by 16. Ideally speaking, the code transition will occur for every, like you can just have a look at in the previous slide. You can see the output code is making a transition at 1 by 16, 3 by 16, 5 by 16, 7 by 16 for every odd half of LSB. So it is making a transition from, okay, output is making transition from one bit to the other bit. So that's what we are trying to see here. So ADC error are defined in terms of the values of Vi at which the code transitions occur. Ideally, these transitions occur at odd multiples of half LSB. So that's what we saw in the previous case. The output will always change when it is odd half LSB, means whether it is 3 LSB, 5 LSB, sorry, 5 by 2 LSB, 7 by 2 LSB, 3 by 2 LSB. So these are the odd multiples of half LSB. The output will change. In particular, the first transitions, that is from 0000 to 001, this will happen at, see here, so this is from 000 to 001, where the output is making a transition. The output is making a transition when the input is 1 by 16. So that's what is given here. So output will, just a minute, there is a transition happening from 000 to 001 when the input voltage is half LSB. See here, when the input voltage is half LSB, which is 1 by 16, output is changing from 000 to 001. Similarly, see here, the last transition from 110 to 111. So we have it here. This is 110. This is 111. So when at what input voltage this transition is happening? This transition is happening at 13 by 16 voltage. So that's what is. So 13 by 16 volt. So that is, okay, VFSR minus 1.5 LSB, because we know that this is FSV. So VFSV and VFSR are having a difference of 1 LSB. It is another half LSB less than the full scale voltage. So that's why it is minus 1.5 LSB. So minus 1.5 LSB compared to VFSR is given by, so since VFSR is 1, so 1 minus 3 by 2 of 1 by 16 happens to be 3 by 16. So this requires some plotting of the graphs on the graph sheet, so that you can able to get all these variations, all these understanding done. So we know that VFSR in this case is 16 by 16 and LSB is given by 1 by 16. If you make that 1 minus 3 by 2 of 1 by 16, so this exactly comes out to be 13 by 16 volt. Now let us see what is this offset and gain errors. So offset error is the difference between the actual location of the first code transition and half LSB. So as you can see here, in this case, so there is a transition happening at half LSB. So if it was not happening at this point, then there would have been some offset error. Since the transition of the first bit is happening at half LSB, in this particular case there is no uh, offset error. Similarly, gain error is the difference between the actual output location of the last and the first transition. The ideal separation should be VFSR minus 2 LSB. So what does this mean is, suppose if the separation between the first transition and the last transition, suppose if you just go back to the previous slide here, see here, this is the first separation. The first transition is happening at 1 by 16. The last transition is happening at 13 by 16. If you actually find the difference between this 13 by 16 and 1 by 16, if that difference is exactly equal to VFSR minus 2 LSB, then we say there is no gain error. Suppose if the difference between the first transition and the last transition, if their separation is anything other than this VFSR minus 2 LSB, then we say there is a gain error occurred. So we shall actually take a few examples to understand this offset error and gain error in the actual graph sheet, and try to find out what is the gain error and the offset error. We'll just take up some examples in the next video. Now, even after both the errors have been nulled, so as we did in the same similar thing we have done in the DAC also, we had some offset and gain error. Even upon setting those errors 0, we had an error like INL and DNL. So even upon making these two errors like offset error and gain error in ADC also, so the remaining transitions are likely to deviate from the ideal values. So we shall see what are the errors that will going to come into picture even upon making this offset error and gain error as 0. So just have a look at these two ideal plot and the typical plot. See here, in the ideal plot, so there is a transition happening for every odd half LSB. Now this is half LSB here. You can see this is, just a minute, this is half LSB. Now you can see at half LSB there is a transition happening. So this is 3 times half LSB. This is 3 times half LSB. So there is a transition happening at 3 times half LSB here. So this is corresponding to 5 times half LSB. This corresponds to 7 times half LSB. So the transition in the ideal case will happen for every odd half LSB. Just see the typical graph. Now you can see it is happening for the first case, it is happening fine. For the first case, it is happening at half LSB, and in this case this was supposed to make a transition here, but it is making a transition here. So it is happening at, this is half LSB, this is 2 times half LSB, this is 3 times half LSB, this is happening at 4 times half LSB. Now since the transition is not happening at odd times the half LSB, now there is a deviation from the ideal plot. So you can see now it is happening over here, and it is not happening at odd half LSB. Now this is the typical output voltage output plot that looks like. So now you can see there is a solid line written. So this solid line exactly passes through the center of that span. Now here there is a dotted line which is written here. This is exactly passing through the center of this typical span here. You can see now it is passing through all half of that horizontal line. Now we shall see what is this INL DNL in the next video. So it is you need to comfortably try to understand what is this ideal plot, when does your output changes. In the ideal case, output always changes for in every odd number of half LSB. This is 1 LSB, 1 half LSB, this is 3 half LSB, this is 5 half LSB, so on. So we shall see INL DNL of ADC in the next video.